Okay, let's just jump right into this explainer and bridge the massive gap between single atomic interactions and the chaotic, highly mathematical heart of a nuclear reactor. Up until now, if you've been following the basics of nuclear physics, we've mostly focused on the micro level, right? Individual neutrons hitting individual nuclei. But today, we're shifting gears. We're zooming way out to look at the continuous, macroscopic behavior of billions upon billions of neutrons moving through a reactor core all at once. Because to actually design a reactor that sustains a chain reaction and safely distributes power, we absolutely need a mathematical framework. That framework is called neutron diffusion theory, and it is literally the quantitative foundation of every single reactor that has ever been built.
Just imagine, for a second, trying to track 10 to the power of 13 individual neutrons flying around a reactor core at any given second. It's a completely intractable problem. Trying to predict the behavior of a reactor by calculating every single microscopic random walk is kind of like trying to understand the pressure inside a balloon by tracking every individual gas molecule. You just can't do it. Instead, we have to rely on collective, macroscopic behaviors.
So to get there, here's our roadmap for today. Tracking the neutron population, Fick's law and diffusion, reactor geometry and flux shapes, diffusion and migration lengths, reflectors and neutron economy, and finally, when diffusion theory fails. All right, section 1, tracking the neutron population. To solve this massive computational hurdle, we're going to build a mathematical toolkit to track this population collectively. Just like we use temperature or pressure to measure a gas instead of tracking individual molecules, we use this absolutely crucial concept called neutron flux, represented by the Greek letter phi. It describes exactly where reactions are happening the most. The big takeaway here is that flux is essentially the fundamental currency of reactor physics. Where the flux is high, the chain reaction is roaring and power is being generated rapidly. Where it's low, the reaction is weak. Understanding and controlling the spatial distribution of this flux, well, that is the entire game in reactor core design.
Moving on to section 2, Fick's law and diffusion.
So, how do we actually figure out the way these neutrons flow? Now, if we wanted to be perfectly rigorous about it, we'd use the incredibly complex bolt-on transport equation. But that is notoriously difficult to solve and insanely computationally expensive. Instead, we bypass it with an elegant shortcut called Fick's law. We literally just apply the everyday intuition of how heat flows from a hot room to a cold room or how perfume diffuses through the air. Fick's law tells us that the net flow of neutrons, which we call the neutron current, is directly proportional to the gradient of the neutron flux. The math simply says that neutrons flow from areas of high flux to areas of low flux.
This brilliantly illustrates how a very simple, relatable gas analogy becomes our diffusion approximation. By combining Fick's law with a basic statement of conservation, meaning the rate of change in neutrons equals production minus absorption minus leakage, we get the neutron diffusion equation. And the amazing thing is, across the vast majority of a thermal reactor's interior, this simple approximation captures the physical reality incredibly faithfully. Let's dive into section 3, reactor geometry and flux shapes. Let's see how this builds into an equation that actually dictates the physical shapes of real-world reactors. Combining Fick's law with a neutron balance gives us the steady-state diffusion equation. We can rearrange this into what's called the Helmholtz form, which features a really crucial property known as buckling. What this tells us is honestly incredible. The shape of the flux distribution is entirely dependent on the geometry of the reactor. The math dictates the exact spatial distribution. In an infinite slab, the flux follows a perfect cosine curve. In a finite cylinder, which, by the way, is the shape of most real-world power reactors, the flux is a product of a Bessel function radially and a cosine function axially. And in a sphere, which minimizes neutron leakage and is heavily favored in weapons physics, it's a sine function divided by the radius. But here's why this really matters in the real world. Because these mathematical shapes show us that a bare, uniform reactor is always hottest right at its absolute center. If you just build a perfectly homogeneous cylinder of fuel, the cosine and Bessel functions dictate that the center would literally melt before the outer edges even got fully up to temperature. Because of that, reactor engineers have to use non-uniform fuel enrichment and carefully place burnable absorbers to flatten this power curve. They put more reactive fuel near the edges and less in the center, which ensures a uniform power output and prevents core damage.
Section 4, diffusion and migration lengths. Let's ground some of this abstract math by looking at the diffusion length. This is simply how far neutrons typically travel from their point of birth to their point of absorption. And just look at the sheer contrast in these numbers. The diffusion length is entirely dictated by the scattering and absorbing properties of the material. In standard light water, a neutron only travels about 2.7 centimeters before being absorbed. But in heavy water, it travels around 170 centimeters. That massive difference brilliantly illustrates why a heavy water reactor, like a CANDU, can have widely spaced heterogeneous fuel channels, while a standard light water system requires its fuel assemblies to be tightly packed together. The physics of the moderator entirely dictates the architectural blueprint of the reactor.
Now, up to this point, we've been sort of pretending that all neutrons have the exact same energy. But in reality, neutrons are born fast from fission at several mega-electron volts, and they have to slow down to tiny fractions of an electron volt to become thermal neutrons. To make our toolkit even more accurate for complex designs, we step up our sophistication. We move from a simple one-size-fits-all one-group theory to two-group theory. Two-group theory writes separate coupled equations for fast and thermal neutrons, tracking how they actually slow down from one group to the next. And in modern commercial reactor physics, using complex codes like Simulate or Parks, engineers use multi-group theory, which tracks dozens or even hundreds of specific energy slices in 3 dimensions.
Section 5, Reflectors and Neutron Economy.
We now arrive at a really critical engineering challenge. How do we keep our neutron economy thriving? If you have a bare reactor, neutrons at the very edges are just going to leak out into the surrounding environment. And because neutrons leaking out contribute absolutely nothing to the chain reaction, they represent wasted energy and wasted fuel. We solve this by surrounding the active core with a reflector made of moderating materials. Things like light water, heavy water, graphite, and beryllium are all used to bounce those escaping neutrons right back into the core. This creates massive reflector savings. By bouncing those neutrons back, a reflected core can achieve criticality at a significantly smaller size than a bare core. In a world where highly enriched uranium is incredibly expensive and subject to super strict non-proliferation constraints, shrinking the minimum critical size of your reactor saves a staggering amount of money and resources.
Fascinatingly, if we apply our two-group theory to a reflected reactor, we discover something highly counterintuitive. Because the reflector region consists mostly of moderating material with very few neutron absorbers in it, fast neutrons leaking out of the core scatter and slow down safely into thermal neutrons. And because they aren't immediately absorbed out there, their flux actually rises. This means the highest thermal neutron flux in the entire system can actually peak completely outside the active core. This thermal flux peak is heavily exploited in research reactor designs, allowing scientists to place experimental irradiation facilities or isotope production targets out in the reflector. They get blasted with thermal neutrons without suffering radiation damage from fast fission products.
Finally, Section 6, When Diffusion Theory Fails.
We do have to acknowledge the strict boundaries of where this trusty mathematical toolkit actually breaks down. Diffusion theory is powerful, but it's not magic. Because it assumes neutrons scatter many times and flows smoothly like a gas, the diffusion approximation completely fails in a few very specific scenarios. First, near strong, localized absorbers like control rods, the flux plummets way too sharply for the math to handle. Second, it fails at sharp material boundaries where the scattering properties change drastically. And finally, it fails near the outer vacuum edge of the reactor. At that edge, neutrons are streaming out, but none are streaming back in. It's highly anisotropic, which totally breaks the fundamental assumption of a smooth gas-like flow.
So the crucial point here is that when we hit these highly complex, localized spots, physicists just have to abandon the diffusion approximation. To fix the math in these extreme local environments, they bring out the heavy computational tools. They use discrete ordinates, which slice up space and angle rigidly, or they use probabilistic Monte Carlo tracking methods, which actually simulate the exact random walks of millions of individual neutrons through the geometry to finish the job. Usually, they'll use these advanced methods locally and then feed those results back into a whole core diffusion calculation. Think about all of this for a second. The exact same intuition that tells us how heat moves from a warm room to a cold room, or how a spray of perfume diffuses in the air, is the quantitative foundation for every single commercial nuclear power plant operating on Earth today. The fact that every reactor ever built relies on this elegant, simple diffusion toolkit really leaves us to wonder just how many other massively complex, seemingly impossible physics problems are out there, waiting to be decoded by a simple change of perspective. Keep that in mind as you look at the world around you.